Okay, we're underway. Right, so on this lecture we'll just be finishing off the... Oh, a few more people coming in, okay? Just let them settle. So we'll be finishing off the AI material that I mostly did on Monday. I think that means there are 13 of you here now. Right, so on Monday we rattled through a bunch of stuff about AI, including like the broad parts of the field, you know, Turing's aspirations, and a little bit of the more kind of practical things that you have in games, which I still have a bit more to say on. And we finished by speculating that one of the interesting properties that you would want an intelligent agent to have would be the ability to learn. So that's when I showed you some of the war game stuff, whether it's this sort of chatbot that's trying to learn how to play games. That's part of its purpose in life. And we spoke a little bit about possible learning algorithms. It is in fact something that Turing himself mentioned back in 1950. You've seen all this before, so I'm just rattling through it to get us up to speed. And the idea is that one of the ways you learn is by responding to feedback from the environment that tells you whether you're doing well or badly, and you kind of adjust your algorithm based on the feedback. That way, instead of having like a dumb chess program that would always play the same moves at the same time, you'd potentially have one that would learn from its previous success and failures and actually adjust its play style and potentially become better and maybe eventually be, you know, better than the algorithm that was originally programmed into it. And that would be quite cute. So this kind of thing has been kind of played with over the years. So a kind of reward and punishment system is indeed what Turing suggested could be used to train a machine intelligence. You'd start off having a kind of childlike one, and then you would throw life experience at it. There's one way in which this has been done that I did mention on Monday, and that's genetic algorithms, where the way you do the development is you just throw out basically random strategies and you try lots of them, and then the ones that appear to be successful, you create combinations of those, and then you kind of make slight changes, which is like a mutation in evolution, and you do it that way. So just through like trial and error and selection, you can eventually curate algorithms that are good at something. And this is often used for things like locomotion systems. In fact, I think there may be even this beginning to be some game technology that was sort of where, you know, character animation systems that were slightly trained this way. I'm not quite sure if that's right. So that's as far as we got. There's the other way of doing learning systems, which is the kind of more fashionable one now, and that's something called artificial neural networks. How many of you have heard of those? Yes, everyone, right? Now, the very first time I taught a version of this course, my first version was back in 2013, and I had a bit in it about neural networks, and almost no one knew what they were, because they had really just come into prominence. It was in 2012, Google wrote a famous thing called the cat recognizer, where they'd created a neural net that could take pictures and tell you whether it was a cat or not a cat. You know, the internet was very cat obsessed back in 2012, so that was seen as, and it was actually a great breakthrough. So, and of course, since then, neural nets have become a huge thing, and I think I'm not surprised that everyone in a room like this would have heard about them. I wonder how many of you know, though, when were neural nets actually invented?
Back in the perceptron in the 70s.
That's pretty good. You're not right, but the perceptron was one of the key ones. The perceptron was actually done in the 1950s, I think 1956 by Rosenblatt. But the very first neural network ideas were suggested in 1943 by McCulloch and Pitts. Neural networks are ancient. Neural networks are older than transistors. Right? So actually, people have been speculating about this idea that you would somehow simulate brains by, well, that's, you know, the idea is that, you know, brains are made up of these little neurons and they're connected together, and if at some level we could maybe approximate that, it might give you some kind of system that is capable of learning. So the work's actually ancient. It goes back to the 40s. But neural nets have come in and out of fashion several times. It turns out that the early work on them, you know, things were very primitive. You couldn't get much done. They could show that, oh, they can maybe compute certain types of function, but we're not sure how training them was difficult. Hard to figure out how to make them be better at something. Then in the 60s, Minsky and Papert wrote a book, or a paper, and then a book, I think, arguing that actually there were things that, that the simple neurons, kind of single-layered networks that they had then, there were certain things that they couldn't do, sort of theoretically, and that kind of killed the field for a long time. But then in the 80s, some people figured out some better ways to do training algorithms on neural networks that made them work a bit better, so they became popular in the 80s. When I was a student in the 90s, I had heard about them on my own reading when I was a teenager, so I was into them, and I tried to learn about neural nets when I was at uni, but it was a lot harder then because there was no internet and I didn't really know how to access scientific papers. You know, they were hard to get access to these things. But they were kind of briefly popular, but then they faded again. They could do some things. In the 80s, they got to the point where they could do limited things like handwriting recognition for restricted sets of things. They were actually used by the US postal system to sort of automatically read their zip codes and stuff like that. That was the kind of thing that they managed to do in that wave. But they couldn't really get much beyond that. So the whole field kind of collapsed again and went very out of fashion. But eventually, things like the power of modern GPUs, you know, the graphics chips that were invented for games, it turns out GPUs are really good at doing neural net calculations. And you combine that with all the enormous data that places like Google had, you know, indexed, searchable data for like images and stuff. So you could create these huge training sets that are needed. So you need a lot of training data and a lot of computation power to get neural nets to be effective. And that all just started to pay off about 10 years ago. And since then, they've definitely become the new hotness in AI. Okay, so that's the basic idea of a neural net, is simulate a brain. Now, don't take that too literally, though. The whole idea that you're simulating brains, it's kind of a metaphor. I think really biologically informed people kind of don't like this idea that, you know, neural nets are brain-like, because they're kind of like a cartoon version of the brain, much simplified, but it's inspired by the idea of a real brain. Okay, so yeah, I've given you some of the history there. So a neural network, you sort of know what they are. You have these little processing units called neurons that just take a bunch of inputs, and they basically have a weighting on the inputs, so they multiply their inputs by some weighting value and add them together, and then they take that result and transform it into an output, either by saying, like, if you're above a certain threshold, I'm going to fire this neuron, or more typically, there's like a little curve that indicates how much they fire or not. Okay, so this is the kind of thing you would. Sorry, I find it distracting. Forgive me. Right, so here's an example of a kind of very simple neural net where you'd have some inputs where you put in some like initial data. This would be like, you know, pixel colors. If you were trying to identify an image, obviously you'd want more than 3 pixels. So you'd have like, you know, hundreds or thousands of these input pixels. So your pixels come in, or whatever it might be. They then go into this the so-called hidden layer. It's called hidden just because it's neither an input nor an output. It's part of the internal mechanism of the network. And these things come in and they get weighted and added up and stuff, and then they get bounced out to these output ones. And the idea is that with suitable tweaking of the weights of all these numbers, you could compute some function that would take in pixels here and would output something here that says, you know, if this number comes out high, then it's probably a cat. And if this number comes out high, it's probably a dog, or whatever the different things that it might be able to recognize. Kind of a miracle, though, because how can you do that? And that's where the whole process of how you train neural networks to actually make them do these things. At some level, it must be possible, right? Because your brain can look at a picture of a cat and can say, yeah, it's a cat. So there must be some computational process that you're doing. But the thing is, it's hard for you to know what it is. You know, normally when you program, you think about something that you know how to do, and you just write it down very pedantically so the computer can do it. But it's like, I know a cat when I see one, but I would struggle to write a program that tells a computer what because it's like, I would say, okay, it's like this small furry thing, sometimes it's white and sometimes it's black, and it's a certain kind of size, and it's like, yeah, it would misidentify lots of small dogs as cats. And it's like, I do know the difference between dogs and cats, but what is it? I mean, the 4 legs and noses and they're cute and everything. I mean, barking maybe is a clue, but you don't get that if it's a picture. So it's like, how the hell do I know the difference between a dog and a cat? It's like, you know, but you don't know how you know. And neural nets are kind of in that zone that we somehow train them to identify the features that are meaningfully cat-like or dog-like, even though we don't quite know exactly what they are. We just train it. We say, look, those are cats, those are dogs. And every time it gets it wrong, you slap it. And when you slap it, it changes its mind. It changes one of these numbers on the network. And you just keep hitting it until eventually it gets it right. So it's an extremely cruel process, but it produces results. You can't argue with the results. So real networks, the ones you talk about nowadays, deep neural networks, they don't just have one hidden layer. They've got tens or dozens, probably hundreds now of hidden layers. The more layers you have, apparently the more complex sort of things you can do. So that's all what's going on there. Yes. So I basically said all that. All right, so you just take a weighted sum of the inputs, and this is what we think real neurons actually do. You know, neurons have got connections that come into them on the axons that carry signals, and a certain pattern of signals triggers the neuron to fire onto its next link in the chain. So that's sort of the idea. All right, so I've given you the kind of cat-dog story already. Yeah, that's the really simplified version of how they work. Those of you that have actually done machine learning courses might have done it in more detail than that. But, you know, we're only game programmers. So the other big technique that made neural nets practical nowadays is a thing called backpropagation. And this is how the learning algorithm works. That's the link to the Wikipedia page, I think. So basically what backpropagation does is it's how you work out how to slap them. The idea is that basically when it makes an error, like if it says cat when it should have said dog, you have to kind of go back through the link of layers and tell it to change its weights. And you can actually do this in a particular way that is hopefully designed to make it converge to producing good answers without making it forget all the previous stuff that it knew. You know, you don't want it to, if it was previously identifying things correctly, you don't want to mess that up. So you can only change it a little bit. And it's like, how do you do it exactly? One of the guys who pioneered this, called Geoffrey Hinton, has described backpropagation as being a bit like doing the chain rule for calculus, but backwards, to try and go through the network and figure out how to tweak all the parts. So that's basically the trick there. Okay. So of course, neural networks, huge subject, a big active field. If you are keen, there are courses you can take. In fact, there used to be an online one from Coursera, but it turns out they've taken it down, but you can still find it in video form, so you don't get the full course, but you do get a video playlist. So this is how I learned neural nets. Geoffrey Hinton's a really interesting man in the field. He's actually related, he's a distant relative of George Boole, the guy who came up with Boolean stuff. This is his great nephew or some blooming thing. And this is where he kind of talks about his neural networks stuff. Or you can, if you want just one thing, this is a video where he gives a basic overview. This will be slightly out of date now, of course, but it's a good, in fact, well, my goodness, so this is before it got big, right? But it might be interesting as a kind of historical view, because he's one of the pioneers talking about it before it was cool again, if you're into that kind of thing. So, of course, modern neural nets, as I think you know, can do all sorts of things that previously were unsolved AI problems that, like, just 10 years ago, in many cases, we couldn't do, or we couldn't do them well. Things like how to recognize speech. Now, I say recognize speech. What I actually said was, literally, how to recognize speech. That is what I said. But how many of you thought I said recognize speech? Right, I didn't. I said recognize speech. I was very careful. So this is one of the reasons why it was always seen as a hard problem. This is one of the examples we used to use, but why it's hard. Because the problem is that there are lots of ambiguities in the waveforms, as I've kind of said in a previous lecture. Even the gaps between words. You know, we think there are gaps. You go and look at the waveform, the gaps aren't really there. Often people run the words together, especially Icelanders. It's not your fault. I mean, I'm bad as well. I speak too quickly. So it's hard to do it. You have to work out how to parse things into words, which is actually not really information that's in the audio signal. It's all based on expectation. It's the fact that you already know the language is a big part of what you're doing when you hear. That's why you have to be trained. You have to develop an ear. And that's why, you know, when I said recognize speech, from context and because it was written down here, you wanted to hear recognize speech. So it's a hard problem, but we've got good at it now. Other things like recognizing images, handwriting, automatic translation. The very early versions of Google Translate didn't use neural networks. They used the old-fashioned approach, which is where you have, you know, basically a big program that tries to parse sentences and looks up words in dictionaries or does pattern matching, or almost like a chatbot, except a chatbot whose purpose is to convert the text, not to simply respond to it in a kind of dumb way, right? But they found that it didn't take long before these neural network systems produced better results, and they replaced them all. I think even early Siri didn't actually use neural nets, but now it does. You know, they've all just shifted over because the neural nets just seem to produce better results. And things that used to be kind of hand-coded are now being replaced by these trained systems. So that's kind of interesting. So I've kind of told you this, that right at this, when I first gave this course, no one really knew what neural nets were, but it's become a big thing now. This is a good one. Again, this is now quite old, but I was impressed when I first saw this. I think, is this maybe 2014 or something, this one? Yeah, 2014. They took their cat recognizer, the Google Cat Recognizer, and went to the next level where it could identify arbitrary objects in a scene. and then actually produce captions, descriptive captions of them, which you can see would have certain uses for people, blind people or whatever. So you show this picture to a neural network that you've just trained by throwing pictures at it and slapping it repeatedly, and then it starts saying, 2 pitas sitting on top of a stovetop oven. It's like, how the fucking hell did I do that? So, and we don't really know, because it's because the process is somewhat opaque. So it's really a remarkable thing. This is sort of the architecture of it. So it is indeed a layered neural network. It's 2 different types of neural network and a bunch of training data, so that learns to sort of understand what the salient features of objects are. But it's all kind of, look at a little girl in a pink hat is blowing bubbles. Well, she's not blowing bubbles, but it's pretty good. A yellow school bus, apart from the pattern, no, it's not really a yellow school bus, but I can see why it would think that. So it's like, they're not perfect, and you can't trick them. In fact, you can trick them in slightly different ways from tricking humans. Neural nets seem to suffer from different optical illusions than humans do, which is a clue that they're not doing exactly what we're doing, but they're somehow in the same neighborhood. So it's all kind of fascinating stuff. This is an attempt to kind of illustrate what they're doing, because it's hard to understand what the neural nets are really doing, because it's all just a bunch of numbers. So one of the things they got it to do was take some images and identify the things that you think you see in the image, the computer that is, even if it's not confident in them. Like sometimes it'll think, that looks a little bit like a dog, but it's probably not really a dog, that kind of thing. What you do is you run the system on an image and you tell it to identify things that it thinks it sees a little bit of, and then tell it to exaggerate that thing that you think you see, emphasize it, make it look stronger so we can see what you think you're seeing. It turns out if you run this on it, it creates these totally trippy, like LSD hallucinations that show what the machines think they're seeing in the world. And one of the funny things was that a lot of the early training data seemed to have a lot of dogs in it, maybe because they were doing animal recognition. So a lot of these systems, if you run them and tell them to hallucinate, they basically hallucinate dogs, which I think is wonderful. In fact, you know that thing where people can see faces in things that aren't really there? It's called pareidolia, I think. And that's probably because as humans, we evolved to be very sensitive to seeing other humans and identifying human faces. We're very good at it. Like basically, to a first approximation, all people look the same, but we're able to tell quite subtle differences between people. You've got to look at a bunch of trees. All trees just look the same to you, don't they? I mean, I'm sure they're different. They're probably just as different as we are, but we're not good at identifying individual trees, but we're good at identifying faces. So human brains have probably got this bias for seeing faces, so we can see them in things that, where it's just like an inanimate object, but it looks a bit like a face. It looks as if the current level of image recognition AIs see dogs everywhere. actually a range of animals. You can see a lot of birds early on. The forest scenes seem to make you think of birds, so that's the kind of thing that happens. Actually, this one here, which I won't show you, I'll show you maybe a little bit. This is specifically quite dog-based. This was one of the video walking through a grocery shop, and you see it seems to love dog faces. It just sees little dogs everywhere. Very strange. So this is a very recent one that I just saw this year. They're getting even better now, these systems, where not only can they do image recognition, they can then generate images from textual descriptions. So this guy here created this video, and I think it's legit. I mean, I haven't seen the source code, but this is the kind of thing people can do now, where he's taken, I don't know if you know the famous poem Kubla Khan by Coleridge. Probably, maybe as Icelanders you wouldn't study it, and like in British schools you sometimes get taught this poem. In Xanadu, the Kubla Khan, a stately pleasure dome decree, that one. Anyway, old poem. And he just fed this poem in to a system that takes textual description and tries to create images of them and stitch them together. So the computer has visualized poem. It's remarkable.
In Xanadu did Kubla Khan a stately pleasure dome decree, where Alph the sacred river ran through caverns measureless to man, down to a sunless sea. So twice 5 miles of fertile ground with walls and towers were girdled round, and there were gardens bright with sinuous rills, where blossomed many an incense-bearing tree, and here were forests ancient as the hills, enfolding sunny spots of greenery. But oh, that deep romantic chasm which slanted down the green hill athwart a cedarn cover, a savage place, as holy and enchanted as air beneath a waning moon, was haunted by woman wailing for her demon lover. And from this chasm, with ceaseless turmoil seething, as if this earth in fast thick pants were breathing, a mighty fountain momently was forced, amid whose swift half-intermitted burst huge fragments vaulted like rebounding hail, or chaffy grain beneath the thresher's flail. And mid these dancing rocks, at once and ever, it flung up momently the sacred river. 5 miles, meandering with a mazy motion, through wood and dale the sacred river ran, then reached the caverns measureless to man, and sank in tumult to a lifeless ocean. And mid this tumult Kubla heard from far ancestral voices prophesying war. The shadow of the dome of pleasure floated midway on the waves, where was heard the mingled measure from the fountain and the caves. It was a miracle of rare device, a sunny pleasure dome with caves of ice. A damsel with a dulcimer in a vision once I saw. It was an Abyssinian maid, and on her dulcimer she played, singing of Mount Abora. Could I revive within me her symphony and song, to such a deep delight 'twould win me, that with music loud and long I would build that dome in air, that sunny dome, those caves of ice, and all who heard should see them there, and all should cry, "Beware, beware, his flashing eyes, his floating hair! Weave a circle round him thrice, and close your eyes with holy dread, for he on honeydew hath fed, and drunk the milk of paradise."
It's really strange, isn't it? I mean, see, it knows what some of those words mean, and it's got visual references from like caves of ice, with music it did a piano kind of, and it hallucinates them and kind of blends them together in like this weird kind of dream thing. Extraordinary stuff. And in fact, the other thing you can do with neural networks is they can play games now. They've got them doing that. I don't know of any real applications of neural nets in an actual live game yet. We haven't quite tamed them sufficiently.
Wasn't it OpenAI with Dota 2?
Were OpenAI doing a game, or were they doing something else?
Yeah, 5 versus 5 Dota game.
Ah, yes. So they sometimes do make them play agents, a bit like the genetic algorithms thing. So it's true. There's been some attempts to use neural algorithms to play within. In fact, I think StarCraft. They tried to get a neural net that could play StarCraft. But I don't know of like a game that's shipped with neural nets as actually part of the tech yet. You know, the NMAI is neural net based. I don't know of anyone doing that yet. But there was a paper done again a few years ago where a company called DeepMind created an AI that could in fact play Breakout. And it doesn't do it the way you would do it. You know, in the old days, if you wrote a Breakout AI, you take the paddle and you'd make it move left and right to follow the ball and stuff. This does it sort of the fair way, which is the input to the system was just the pixel data. There was nobody telling it what is a paddle and what's a brick. So the input to the neural net is a bunch of pixels, and the output is that it would be told what score it got, and it just had to figure out how to maximise its score by like and it would just basically randomly button mashing, because basically all it could do was simulate pressing buttons on a controller, and it would just like flail at random at first, and then eventually realise that there are certain things that you do that actually help the score go up in this game, and over time it would learn how to do them. Have any heard of DeepMind, the company? Yeah. They were bought by Google. They do this. DeepMind was actually founded by a guy called Demis Hassabis, who used to be a game programmer. I actually met him once many years ago. He used to work on things like the theme park games, the Bullfrog simulation games from back in the day. And after a period of that, he went back to university and studied neuroscience and learned more about neural networks, and then set up a company called DeepMind to explore this when it was just getting fashionable, and started producing stuff like this, and then sold his company to Google for $400 million. Lucky him. Well, I'm doing this. So you see over time the neural net starts to learn how to play the game, how to move the paddle, to match the ball. It just seems to it got the idea. The cute thing is that if you play it for long enough, it doesn't just get the basic idea, it starts to learn the tricks. It starts to learn that it's good to go up the side, so that way you can bounce along the top, which is how you get high scores at Breakout. So eventually it figures out. You see, it's sort of like trying to go up the side wall, as if it's kind of learned that that's a productive technique. There we go. That's the killer strategy for Breakout. There you go. This got quite a lot of publicity at the time when it was done, which again is a few years ago now. But don't believe the hype. There was a little bit of, oh my god, the AIs are taking over type of stuff. It was good at Breakout, but it's not good at everything. They ran it, because the idea is it just takes pixels as input, so you can feed it like any game and see whether it can learn how to play that game. Some games it does better than others. For example, it was rubbish at Space Invaders. It just couldn't seem to learn anything useful about Space Invaders for some reason. I read the paper. You can read it yourself if you're into that kind of thing. You're maybe not sure quite ready for reading papers, but it's what real computer scientists do. So here's something from the paper where they tried it against various games, and their thing was called a deep QNet, was what they called it. Compare that against various other systems, including humans, and you'll see that for Breakout, it's actually really good, 168 on Breakout, whereas humans only got 31. But it's rubbish at Space Invaders compared to humans. It's rubbish at Sequest. So it wasn't. It was good at Pong though. Again, Pong and Breakout going to be siblings in this regard. So neural nets can do some things, and then there are other things that they can't quite do yet. So that's all very fascinating, but that's as much as I can tell you about that. We're now going to have to just plonk back down to earth and talk about actual, really existing games tech, which is not yet quite that interesting. So it's the one big traditional thing in game AI that I need to talk about, and that's route finding, which is just one of the main things you'll end up doing. So one of the standard problems in game AI is just how to get, or AI generally, is just how to get from A to B. Actually, getting from A to B is easy. A and B are next to each other, simple. But getting from A to Z is a harder problem. That's sort of a joke, So how do you do it? How do you navigate from A to Z? Well, there's a naive algorithm which is roughly as follows: you're at A, point towards Z, keep going that way, and sometimes that's going to work, right? Like if you're lucky, that'll work. Sometimes the straight line is okay, but of course if it's not, you have to, when you hit an obstacle, if you do the straight line thing, you kind of route around the obstacle somehow. And there's a classical thing called wall hugging that used to be used, where you basically want a straight line, and when you hit an obstruction, you would just like hug the wall on like the left side or something like that. You would just edge around the obstructions until they went away and kind of kept trying to come back. And again, sometimes that works, but you can also contrive situations where it won't work, where a wall hugger will end up going around in a circle or something like that because it's too dumb, right? So wall hugging is like, actually in real life it's not too bad. If I look at Halgenskirke, I look at it and I basically go that way and try not to bump into any cars and stuff. And if there's a house in my way, I kind of like sidestep a bit, but I just keep pointing in the general direction. You usually get there, right? But there are some things where that doesn't work. Yeah. So that's why we need better route finding algorithms. In fact, how many of you have done route finding in other courses? Do you already know stuff like that? So, oh yeah, okay, cool. But how many don't? How many don't know any route finding yet? A couple. All right. So one way to think about planning a route is it's not unlike what we were talking about playing chess. When you play chess, it's like, you expand the game tree. You think about what's the next move and what's the next move after that and what's the next. And you just keep going until eventually you think about a lot of moves and you pick the one where you're going to win and you do that. In a way, a route's a similar problem. It's like, every moment you have to step in some direction. And you do it, and then you say, okay, am I any better off than I was before? Am I closer? And you step again, and you kind of just try and keep going. Sometimes, usually you'll want to get closer to the thing that you're aiming for, but of course sometimes if there's an obstruction, you might have to temporarily get further away in order to go around it and come back. But that's just what you do. You kind of explore this tree of possibilities. So you have like a route tree as analogous to a game tree. So that's roughly the idea. But if you do that, even if you only have a fairly simple system, maybe you can like move in 8 compass directions. That means your first step can be one of 8 steps, and then your next step is one of like not quite 8 steps because you shouldn't go back the way you came, but it's nearly 8 steps. So now you're up at 64, and then it's times 8 again, it's times 8 again, and it gets very big very fast, right? So it becomes very exhaustive, which is a pain. Realistic maps, you're going to have multiple paths that might work, and lots of so it's a big search problem. It's really kind of tedious if you consider all the possible paths, including like very meandering ones that will eventually get there, but they're obviously not the smart way to get there. So what you really want to do is you want to find the shortest path between your 2 points, your start and end point. And the basic way you do that is you grow your solution of your like imagined path, and you just preferentially expand the nodes that are currently the cheapest paths, the ones that look the most promising. That's a thing called Dijkstra's algorithm. So if you do any algorithms classes, you'll, or suitably advanced ones, you'll come across Dijkstra's algorithm, right? So you can just read in a bit more detail than I will give you. But that's basically the idea is it's expand a search contour, and at any given time, you've got a bunch of nodes that represent partial paths that you've thought about, and just take the one that's currently the shortest one, because that in some sense is the most promising, and then push that one a little bit forward until it's no longer the shortest one, at which point you switch to the next shortest one, and you just keep trying to expand the shortest paths. And then eventually, if you do that, one of those paths will reach the end point eventually, and it will be the shortest one, because that's by definition, kind of by design. So that's Dijkstra's algorithm. So it looks like this, right? So you're expanding these paths. Every time you take the currently shortest path and you go one step beyond, but you see it's going out radially because it's trying like everything. When it counters obstacles, that means it can't really do very much, so it starts to favour these other paths, and it keeps exploring round and round. So it's got this big radius that it's doing, crawls around here, and eventually, because it's filling the whole space, eventually it will get to the end point. And when it does, it then backtracks. Once it finds it, it says, okay, whichever guy found it, we now backtrack from that to the start. And it turns out that was the path it picked, right? So it's chosen a fairly intelligent path, and it did it by thinking about lots and lots of paths, and then eventually narrowing in on the best one. But it seems quite good because it didn't do anything dumb. It managed to kind of walk around this obstacle, but it did it by thinking about a lot of dumb things, including thinking about walking right into the corner here, which is like kind of you look and think, well, that's dumb, but it had to think about it because it doesn't know. Maybe there's a little tunnel in here. Maybe there was like a secret shortcut or something. So it has to think about a lot of stuff, but when it gets there, it eventually can work backwards and identify the nice, fast path. Okay. In fact, Dijkstra's algorithm is used inside EVE Online. It's how when you're calculating if you do a trajectory, if you're trying to work out the route from one star system to another, again, there's like a graph of star systems. They've got warp gates between them and stuff. And the arbitrary kind of mesh route, it uses this to work out the route between star systems. So I'm showing you there on a regular grid. It's slightly easier to understand it that way. But in practice, game maps are often done on a graph rather than a grid. So instead of it being like totally regular squares, you have things like this instead, where you have landmarks and sort of implied path between landmarks. Right? So in real games, if you have like a fairly open environment, it's often marked up this way with something called a nav mesh, where you just put key points on it, and the AI tends to navigate through those key points. But it's the same thing. They've got points that get distances between them, and it just searches out from the beginning point, and it adds up the length of the path, and it just keeps exploring until it finds the best one. So nav mesh in the game is going to look something like this. This might be your real polygon geometry for your level, but polygon level geometry is too complicated for searching against. It would be too slow. So you put these, you take each kind of sector of your map, and you put maybe a hotspot inside each of these little segments, and those become basically a kind of invisible network of paths that the AI can sort of see and use to figure out what it's doing. You can either use like a midpoint like this, or you can use edge points as more like doors, doors between these little invisible segments, or here you put them in the center of the segment. You can do it either way. Okay, but you can do better than Dijkstra's algorithm. As you saw with Dijkstra, when we did it on that little L-shaped obstruction, it spent a lot of time doing dumb stuff, like going into the corner that was obviously stupid. It also spent a lot of time searching in the wrong direction. If you notice that it searches in every direction, and that includes searching totally away from the endpoint, because in theory, the only route might be like a circuitous one, where you have to like back out and go right round the top or something. So it has to search that way. But most of the time, it's totally stupid to search in the opposite direction to where you think you're going, usually. So the thing about A-star search is it tries to finesse Dijkstra by trying to, rather than pursuing the shortest path at any given time, it pursues what it thinks is the most promising path, which is not quite the same. The way it works with other path is promising, is it works out its length plus an estimate of how far it thinks that path is from the endpoint. And this way it kind of biases itself in a direction that seems like a sensible direction. So it produces a more intelligent search. So this is called a heuristic search. The heuristic is the idea of it's a rule. It's not a perfect rule, but it's like a useful rule of thumb. And the heuristic for A-star is try and go in directions that look as if they're closer to the endpoint, because that's probably a good idea, even though it's not provably a good idea. So that's sort of how that works. So Dijkstra explores all the nodes, which is thorough, guarantees that it will find the shortest path if it exists, but it can be inefficient in a certain sense. All right. So the point of A-star is to say it pursues the most promising node, but you don't magically know what the most promising node is. If you really knew, you'd already have solved the problem, right? You don't know what it's like. The algorithm is at any given point, take the best possible move. Thanks very much, dude. It's like, duh. So you don't really know the best move. You guess what the best move is, but the idea is that's kind of better than nothing, right? So you guess. That's what a heuristic is. So you end up with this. So you can see this one. It kind of tried to go in a straight line. It didn't waste its time searching away over in the back, because a straight line is usually the best thing. But hey, guess what? A straight line wasn't great in this situation because there's this obstacle. So it has to actually recover from that, and now it goes round. But you see, it got there much more quickly, right? It took a much more direct path. It didn't waste its time searching out here, which is like obviously kind of stupid, because why waste your time out here? So this is what A-star does. It just takes Dijkstra and gives it a bit more purpose. It says, look, for God's sake, go forward, you idiot. And that tends to shape it to be better. And a lot of games actually use this in games where you've got like a real character doing route finding, where the heuristic is work out the straight line distance to the endpoint, which is easy to do. You can't do that in a space game like Eve, because it's all through warp tunnels and it doesn't have an obvious geometrical interpretation. But in ordinary games that are set on like a map, you generally use A-star. Again, you go back to the tank game I did in the 90s, we used A-star. When the tanks are trying to route towards you or towards their home base, they actually run A-star search. So that's, in fact, they actually run a slightly better version of A-star search that I invented, where in order to make it a bit faster, they do the search from both ends and then they meet in the middle. And that, instead of having like one search here that expands all the way until it eventually gets to the end, it's like it starts from here and here and they meet in the middle, and that sometimes can find the path more quickly. It's like as if it constrains it at both sides instead of having it. So that was something that we played with. I think other people have come up with that idea too, but I did it independently when I was a nipper. So here's an example of A-star in action, where you can see this algorithm being applied. Painting. So the blue is a bunch of obstructions that they're painting between, I think it's starting from white and trying to go to black, or one or the other, right? It's white and black are the starting endpoints. It's painting a bunch of obstacles that get in the way, and then you'll see A-star trying to fill the path by starting to do it as a straight line, but when it can't, it bleeds around it in a reasonably intelligent way. I mentioned A-star, classic algorithm, very lovely thing. It's actually quite hard to write it correctly. It's easy to just make a lot of silly bugs when you're doing it, because you've got all these open nodes that have to be investigated, and then closed nodes, and it can be very bug prone. If you were to write it, you would want to write something like what that guy did there, to give you a nice environment where you can test it and actually check that it's working. Because if you just test it by throwing it into your game, you won't really know whether it's working. It might be your bad guys are just a bit stupid, and you don't know, is that bad route finding, or am I just unlucky? It's hard to know. So you really would want to try and write a good test harness for A-star, just because it's so easy to fuck it up. It's also easy to make it use lots and lots of memory. So if you ever have to do it, be careful. It's not an easy thing to write, even though it's like a well understood algorithm. Okay, despite my best efforts, I think I'm running late on time here. Never mind. It's fun though, isn't it? Right, so that was A-star. A-star, as you saw, if you looked at those paths, though, actually, in some ways A-star is too good, because it will find almost the perfect path between two spots. That would include, on a general game map, that would include things like, being able to, you see, when it does the search, it's basically looking ahead, isn't it? It's exploring the whole map, including parts of the map that it doesn't necessarily know about. It works out how to get out of dead-end traps and stuff like that. But it's but a real person wouldn't be able to, psychically know that that was a dead end and avoid it. A real person would actually go into the dead end sometimes. So it makes search more realistic in games. We sometimes do a thing called sensory search, which is, or that's what I call it, where you're doing something a bit like A-star, but you don't let it go beyond what it could actually really know. So you constrain its knowledge of the map to what it could potentially really see. So if once the route starts to go around a corner that the AI hasn't got line of sight of, you don't let it keep going, because it's I don't know what's around there, and it'd be unrealistic if it did. So you sometimes do that. You simulate having imperfect knowledge where they've got a limited cone of visibility, and you constrain what they can do, and that makes them be a bit less magically brilliant, which is sometimes necessary, because otherwise the route finding could actually be too good. It would make your enemies unrealistically effective. Okay, so yeah, we're nearly at the end. Right, so we learned a bunch of stuff. Let's go back to Turing. I like him. So Turing said, so remember Turing's paper was about, can machines think? But some people have said that the question, can machines think, is actually kind of meaningless. It doesn't mean any more than, can submarines swim? It's submarines do traverse the underwater environment, but whether we call that swimming is a kind of matter of linguistic convention. In English, we don't call what submarines do swimming. Submarines don't swim. Right, but what do aeroplanes do? They fly. But they don't flap their wings, right? So we call it flying, but it's not flying in the way that birds fly, and submarines don't swim in the way that fish swim. So to some extent, it's you have a problem to solve, and the question is, what name do you give to that problem? So computers can do things like image recognition now, which people can do as well. Do you say that they're intelligent because they can do that, or do you just say no, they can solve the image recognition problem? And is that thinking, or is that just doing some task? So sometimes it's a matter of what we choose to make the words mean. So you have to bear that in mind. And we Turing knew that. That's why he came up with the Turing test. The Turing test was an attempt to kind of define thinking, and he defined it as to have a plausible conversation with someone for 5 minutes. But I argued on Monday that that's actually not good enough, because you can indeed create bots that can just about be plausible for 5 minutes, but we know they wouldn't be plausible for half an hour, and we know that they don't really meet our definition of thinking. So we have to find a better one. So it's kind of the goalposts are shifting. The other thing that people say about AI is that AI is the set of things that computers can't do yet. Right? It used to be that just being able to recognize speech was seen as that was an AI problem until we could do it. And now it's like, yeah, okay, it's good. I mean, I like the fact that they can recognize speech, but it doesn't seem like a miracle anymore. But it used to. When computers couldn't do it, it seemed like it was a really interesting AI problem. And within a year or two of it being done, it's like, yeah, it's not AI though, it's just stuff that computers do. So there's this big question though, are thinking machines even possible in principle? And I sort of think they are, that if you were, in theory, you could simulate a brain-like thing in a computer. It might be very hard, it might be too hard for humans, maybe humans aren't clever enough to do it. But to me, it seems like theoretically it would be possible, and that's what Turing thought too. So Turing said, this is only a foretaste of what is to come, and only the shadow of what is going to be. We have to have some experience with the machine before we really know its capabilities. It may take years before we settle down to the new possibilities, but I do not see why it should not enter any of the fields normally covered by the human intellect and eventually compete on equal terms. And that was Turing in an interview from 1949, just before his paper. So he thought it would all happen. Of course, he didn't live to see it very much. He died in 1954, I think, 53 or 54, and he was only 41 at the time. He was quite a young man. Died of I don't know the story. Died of cyanide poisoning, possibly suicide, possibly an accident, possibly something else. So we don't know. But so that big paper was kind of one of the last things he maybe did. So this is the point where I jump into war games. How many of you got around to seeing it? Just of interest? Oh, that's good. So you know what's happening. For those of you who don't, in war games, the little AI called Joshua has been trained to play games that teach basic strategy, things like noughts and crosses, chess, poker, and so on. But ultimately, it was created to solve the problem of strategizing for nuclear war. So the idea is that they've been building this system, treating nuclear war as just a kind of very elaborate type of game that it has to try and compute what the optimal strategy might be so that the Americans could win. Unfortunately, the machine doesn't quite understand the reality of nuclear war. It just thinks it's a game, which is a bit of an oversight on the programming team. And it's got to the point in the story where it has been told to work out how to play nuclear war, and it's trying to do so. It's also trying to decrypt the launch codes for the missiles so that it can give the orders. The orders used to have to go through humans, but they fixed that problem. They took the humans out of the loop because humans weren't reliable enough. And this is it, where it's got to the point where it's trying to come up with a strategy to win World War III.
Put the list back up.
No, we already tried that.
Put it up.
Yes, put it up.
It's not on the list.
What's not on the list?
Go ahead.
It's got to be in there somewhere.
Tick, tack, toe.
You're in. Order to disarm the missiles.
No.
5 numbers. It's got half the code.
One?
Put X in the center square.
No.
Six up.
There's no way you can win that game.
I know that. It doesn't. It hasn't learned. Is there any way to make it play itself?
Yes, number of players 0.
Come on. Learn, goddammit. system.
9 numbers. 10, it's got the code, it's going to launch.
Colonel, kindly call the SAC, get me a launch status report. Major Dave, get me the president. Yes, sir.
Go wrong. What? It was 1983. Nobody knew any better.
How you doing, Colonel?
Sir, all landlines out of the mountain. They're dead. I'm trying to break through on satellites.
Okay.
What's it doing?
It's learning.
Greetings, Professor Falcon.
Hello. Joshua?
Strange game. The only winning move is not to play. How about a nice game of chess?
Okay, I'll let you watch the very final part of it in your own time if you want. So that's just about the end. A few end notes here you can look at. Did you notice Iceland appeared on the list of strategies? Yeah, it's actually there twice. There are 2 Iceland strategies. Yep. This is another good film about insane computers on spaceships. Very good. Dark Star, John Carpenter, the guy who did The Thing. It's a good one. And here are some cautionary tales about AI. Human level AI is 15 to 25 years away and always has been. It's true, we always think it's coming and it's never quite happened. At the end of this one, I always try and look at the latest results of the Loebner Prize, which are usually really bad. But actually, the 2019 one is not bad. You go and look at it, it's like, it wasn't appalling. I still don't think they've cracked the problem, but there you go. There's also 2014's Trollbot. It's pretty funny, just for total giggles. I'll show you what Trollbot has to say for itself. It does really seem to have absorbed the, oh come on, this worked last night. Ah shit, I had to edit this link. I had to use the Internet Archive. Never mind, you can find it yourself. Basically, Trollbot is like the soul of Twitter. So that's all I need to say about that. Okay, so we finally got to the end. I did overrun. Never mind.